When we've talked about building general solutions, where we take one solution, y1, another solution, y2, and build the general solution by making some linear combination of those two things, there's an important idea from linear algebra we need to bring back. If you haven't seen it before, we're going to briefly introduce it here. But the idea is somehow that y1 and y2 are fundamentally different. They're not the same thing in disguise. And they're not the same thing in a very particular technical way here, which is that they are called linearly independent. So, as a brief recap, if you've seen this before, or a brief introduction if you have not, two functions somehow are fundamentally different or linearly independent, so different in the specific way, if and only if, when I take y1 and I take y2 and I try to make them essentially cancel out each other. What we're looking for here is that I add them together and get 0. So think of x minus x would cancel out to get 0. The functions are independent if the only way to get a 0 out of this is by combining them with coefficients of 0 and 0. So in other words, if I can't make y1 and y2 cancel by themselves, the only way to make them cancel is by multiplying them both by 0, in which case y1 and y2 don't really matter. That's when two functions are linearly independent. If I can find some combination like 5 of this minus 2 of y2, if those cancel out, then somehow the functions are the same or have some kind of shared property because they can be used to cancel each other out. So, for an example, if we look at sine t and cos of t minus pi over 2, we notice right away if we graph them, we'll try to graph that a little more square. There we go. The sine graph, of course, is the graph that starts at 0, has period 2 pi. That is sine of t. Now the graph of cos of t minus pi over 2, well, cos starts usually at 0 and then goes down. But if we've shifted it to the right by pi over 2, which is what that minus pi over 2 will do for us, it'll mean the peak occurs here at pi over 2, which is coincidentally exactly where it would have occurred on the sine graph. So our sine graph and this new shifted cos graph are in fact the same thing. So in fact, this is actually equal to sine of t. So if we ask, are sine of t and cos of t minus pi over 2, the shifted version of cos, linearly independent? Are they really? Well, of course they're not very different because they're actually identical. And what we can do is take one sine of t. So what we're trying to do here is build this form here. Is there some way I can combine y1 sine of t and, well, if I put -1 of this cos thing, cos of t minus pi over 2, well, of course that's going to equal 0 because I'm going to have sine of t minus, well, we said that was identical to sine of t, and we're going to get a 0. So this is our a value, this is our b value, and since a and b are not equal to 0, but we still get a solution equal to 0 overall. We cancel everything. These are not, so let's be specific here, these things are not linearly independent. So I'm just going to move this over. There we go. Sine t and cos of t minus pi over 2 are not linearly independent. And most functions that we're going to see that look different are going to be linearly independent. For example, sine and cos of t, same thing with no shifting, would actually turn out to be linearly independent. Now, that whole process that we just went through to show that two functions were linearly independent, or weren't in the last case, turns out to be pretty tedious in practice, so we're going to look for an alternative, and it also comes from linear algebra. We're going to consider two different functions, and we want to know, hey, are they linearly independent or not? And what we're going to do is compute the Wronskian. So this is named after a mathematician. And what it is the determinant of a particular 2x2 matrix or array, where we put the two functions in the top, and the next row is the first derivative of the of each of the two functions. Now the key thing out front is the determinant. If you've seen algebra before, this isn't news, but the determinant, for those who haven't seen it, of a 2x2 matrix is simply the product of the top left corner and the bottom right corner. So what we get here, minus the product of the upper right and the bottom left. So y2 and y1 prime of x. Now the question we need to answer is, why would we invent such a thing, this determinant of this particular combination? Well, here's the idea. If the Wronskian is non-zero at some point, then y1 and y2 are linearly independent. So why would that be true? So we're saying there's a test. I can find this determinant here, and notice here it's at any point, at some point, as long as it's non-zero somewhere, then we're claiming that these two functions are linearly independent. Where does that idea come from? The proof doesn't really tie into the use of it, but it's worth seeing here because it's got some nice tie-ins to linear algebra. So what we're trying to work with is the test for linear independence. And that's that c1 y1 plus c2 y2 equals 0 has only c1 c2 equals 0 as a solution. All right. Well, that we can write in matrix form. We can write y1 and y2 times c1 c2 equals 0. In fact, if you do your finger walking, y1 c1 and y2 c2, when we add them together, we should get 0. It's the same condition. And we're going to add these other ingredients here for generality later on. And hey, we're actually in business here because we're concerned whether c1, c2 are the only possible solutions, if they're equal to 0 is the only possible solutions. c1, c2 equals 0 are the only solutions to this. To have a right-hand side of 0, basically the only way to make that work is if c1 and c2 are equal to 0, or the rows y1, y2 is not linearly independent from, or is a scaled version of the second row, which is y1 prime, y2 prime. Or another way to say that is, there's a test for that, which is that the determinant, this part here, is all together, or the determinant of the matrix is equal to 0. Up here, the solution can only be c1, c2 equals 0. That can be the only solution if the determinant of the matrix that we just built is not equal to 0, or the matrix here is invertible. There's some lovely, lovely linear algebra with this. If you haven't seen it before, please do take a look at basic matrix algebra and the idea of solutions to linear systems of equations. So the idea is we have two outcomes that are possible here. Either c1 and c2 are the only possible solutions to this system of equations. That happens if the determinant of the matrix is not 0, or the matrix is invertible, so there's a unique solution. Or there's the other case where the determinant is 0, in which case somehow y1, y2 in this row here are scalars of each other, scaled multiples of each other, and that is where things break down, where things are not linearly independent. We can cancel them out. So that's where the Wronskian comes from and why we use it. It's not how we use it, though, in practice. So let's take a look at an example. Let's take x and e to the x and simply ask, are they linearly independent functions? And we're going to test that by test to see if the Wronskian of x and e to the x is not equal to 0 for some x. If it is, then we've shown they're linearly independent. If we can find what the Wronskian is, show it's not 0 somewhere, then we have done our job. So how do we test that? We actually compute the Wronskian. This is our y1, y2. and we just put them into matrix form. So we're going to take the determinant of x and e to the x. The second row is simply the derivative with respect to x of each element, and the derivative of e to the x is e to the x. Then we say, well, what's the determinant? The determinant is this weird product, diagonal times diagonal, x times e to the x, then minus the other product, minus 1 times e to the x. And that simplifies to e to the x times x minus 1, and that's not equal to 0 for most x's, actually. Most x. In fact, if you want, it's actually not equal to 0 for all x, except the only way to make that equal to 0 is x equals 1. That makes this part of the element 0. So have we seen the Wronskian is not equal to 0 for some x? Absolutely. Check. Which tells us right away that x and e to the x are linearly independent. And so if we were building general solutions and we found one solution was x, the other solution was e to the x, we can combine those two safely with constants out front and have the general solution. We'll see that through the next, through a few following examples.